So yesterday was day one, and now we're going to talk about solving systems of linear inequalities, and we're going to just continue on from where we did yesterday. So yesterday I covered this number 2 and the got it number 2, and then covered this word problem, and this one was about fundraising. And I thought, well, that's a good place to stop, because one word problem yesterday will lead to one word problem today, so both groups get to see one word problem, and then we can finish up the rest of these notes. There's not a whole lot left here, and then you can have some work time to work on the assignment today. So now I'm going to make you hungry. A pizza parlor charges $1 for each vegetable topping and $2 for each meat topping. You want at least 5 toppings on your pizza. You have $10 to spend on toppings. How many of each type of topping can you get on your pizza? So I want to do the same method that I talked about with the classes yesterday, where the book has this relate and define and all of that stuff. But after teaching this for 24 years, it seems like almost every student can understand, let's find a total and let's work our way towards that total. You are not going to get out of word problems on this test. There are going to be word problems there, so you can't skip them. If you do, you're going to see in Schoology, I left you a little comment. You got to show your work on this one. A lot of them are FAQs, so you need to watch the FAQ video and listen to it so that you can figure out how we set these up. So here's what I'm going to ask you to do. I want you to read through that a time or two, and I want you to find me 2 totals. Did you find one in? 5 toppings. Now, what I need to do next is figure out, is it exactly 5, or could I get more than 5? Could I get less than 5? It says you want at least 5 toppings on your pizza. So, could I get 4 and be happy? No. I'd be happy with 5. I'd be happy with 6 and 7. So this should really be greater than or equal to. Now, this was about toppings. And that seems like something really minor, but that is actually huge, because that means everything else in the equation also has to be about toppings. So I want you to look back. How many different types of toppings did we have? Just the 2, right? Veggies and meats? Well, let's let that be. In fact, did they say veggies and meats? Because then we could use V and M instead of X and Y. That might mess some people up. Let's just use X and Y. So we'll have X plus Y, where X is the veggie toppings, and Y is the meat toppings. Now, like I said, the only other information we got was they want some of both. You know, that was it. It didn't say they want twice as many vegetable toppings as they have meats or anything like that. There were no other numbers for us to deal with. All right, now let's go back and let's see. I'm going to color code. Everything with that specific inequality will be done in red. So now I'm going to switch because I want to find another total in there. Now, how do I know there has to be another one? Because we're talking in Chapter 3 about systems of equations and inequalities, and that means we have to have more than one inequality at a time. You found it, Haley? $10. Now, that and the fact that you said the label was really important. So this one's about money. So now I think, okay, so I'm going to need to know something about money and vegetable toppings. Did they tell us something about money and veggie toppings? $1. They must have also told us about the cost of those meat toppings too, right? How much are meats? $2. Now, you have $10 to spend on your toppings. So would you be happy if you only spent 9? You have money left over, right? If you spend exactly 10, you'd be happy. How about 11? Oh, then you're going to cut into the tip, right? Because you're going to have to take money out of that. So this needs to be less than or equal to 10. So I was explaining to everybody yesterday that the book has a method where they kind of go through these boxes of relate, define, and write. And if that works for you, that's fantastic. Then you don't need to worry about this. But when I'm teaching about word problems, I'm going to stick to talking about totals. And how do we get that total? Because most everybody can follow that. All right, there they are. Now, I need to know what kind of numbers do I have to put on this thing. And to do that, I need to know how it's going to be graphed. So I'm going to color code. This was my red. And this is where we pretend that it says equals, because we want to know where are the points that are on this graph. And this is in standard form, ax plus by equals c. So the fastest way to find those 2 points would be find the zeros. And that's the thumb method, to figure that out. So if x is 0, and I put a 0 up here, it says y equals 5. Well, it would have to be 5 to be equal to 5. And basically that says if you don't get any veggie toppings, then you can get 5 of the meat toppings. Well, how about if we don't get any meat toppings? How many veggie toppings could we get? All 5. If you go vegetarian, get all veggie. Maybe you love meat, go all meats. So there's the first one. But I also have a second inequality, and I have to make sure I can graph that one on the same numbers. So this one was x plus 2y, and then again we're going to use equals 10 to figure out how far we need to go with this one. And that's standard form, so we'll find the zeros. So if we don't buy any veggie toppings, how many meat toppings could we get for our 10 bucks? 5 of them, yeah, because 2 times 5 would be our $10. And remember, that's all we had for the toppings. We don't get any of the meat toppings. How many veggies could we get? 10, yeah, because that would be $1 per topping. So this tells me I have to be able to go to 0, 5 on the y-axis, and I have to be able to get to 10, 0 on the x-axis, because I'll definitely be able to graph 5, 0. Which means I really only needed this portion of this graph. Because you can't have a negative amount of toppings. You can't walk into any of the pizza places in the area and go into Domino's and say, here, I brought you some green pepper, give me some money back. It doesn't work that way, You have to stick with the positives. So I'm going to graph my 0, 5 and my 5, 0 from my red inequality. And I am going to label those. And connect them up. And this time I'm not putting arrows on my graphs, and that's because this is real life and you can't order a -3 veggie toppings. That's just not okay. They're going to look at you like you're crazy. Now, sometimes when you talk about these, it's easier because they're word problems. Let me give you a for instance. Do you remember when we talked about being happy with the amount of toppings? Would this person be satisfied if they didn't get any toppings at all? No, they wanted 5 or more. So they've got to graph out this way. They wanted lots of toppings. Lots of them, if possible, for the money they have. And then I graph my green at 0, 5, but this time 10, 0. But that one was about money. Did they have an unlimited amount of money to buy their pizza? No. They said $10 is it. So this time I can't go out there where you can buy whatever you want. I have to go in here. And just like we talked about 2 days ago, we're going to overshade that middle region because that's the region that has both green and red. And in there, you'd say, okay, well, we have some choices. We could order 6 of the veggies and 1 meat. We could order 5 of the veggies and 2 meats. You know, anything inside that blue region is something that they will be able to order because it meets the restrictions that they have. You know, don't have an unlimited amount of money. Got to keep it within this region. Now, yesterday's lesson and so far today's just involved graphing lines as inequalities. And we know we can also do V-shapes because we just tested you on that from 2.6 to 2.8 and you did really well. So the next step would be, what if we have to mix in lines and absolute value stuff at the same time? Well, that's no big deal. We know how to graph these. So I'm going to color code. And I will graph y is less than or equal to 3 in red. And then I will graph my absolute value in blue. And any math that I do for them, I'm going to do in the exact same color. So it's all very easy to follow when I look at my notes later. Oh, well, this one's interesting because to graph it, we'd think of it as y equals 3. So if I karate chop the big y-axis that's in the world, I'm going to be karate chopping this way. That's a horizontal line. And it is solid because it does have an equals bar. But it didn't say equals, it says less than or equal to. So now I have to figure out where are the y values that are going to be less than 3. Should I shade up or should I shade down? Yeah, down. These are the less thans, down here. So that one's already done. Didn't have a ton of work that I could show for that. This one, to graph it, I want to think of it, pretend it's equals for a minute. And I think it will be really helpful if we write that formula down again so we can remember what that's going to do for us with our A, H, and K. Can you tell me where the vertex of that V is going to be? Haley? It will be at 1, 0. Yeah, that X is always the opposite. So our vertex is at 1, 0. What's the slope of the right side of this graph? One. Exactly, because there's a little imaginary 1 sitting in front of here. So 1 over 1. So for the right side of our V, from the vertex, we'll go up 1 and right 1. I'm going to do that so I have quite a bit to aim at there. And this one was solid. It did have an equals bar. And then I just use that slope backwards for the left-hand side. So up 1 and left 1. Oh, I missed one, didn't I? I went over 2. Let me fix. That's the smart board with all of the shadows that mess with you when you're up here. There we go. That's better. Now, that one was greater than or equal to, but just as easy to test a point, right? Was 0, 0 inside or outside our V? Outside. So let's check 0, 0 in here. So what's 0 minus 1? Negative 1. What's the absolute value of negative 1? Is 0 greater than or equal to 1? Well, we're not shading outside the V, are we? We're going to have to shade inside the V. Which shows us exactly where we need to do our double shading. Because only this region right here which happens to show up as a triangle, has both red and blue. So that's where the solutions are. And because these lines were solid, any points on the border of that triangle would also be included. So again, just like yesterday when we were going through this, the class said, well, we already know how to do all this stuff. We do. It's just that last little step of where do they overlap, because that's where the solutions to the system are. They have to work for both. All right. I would like you to help me out much more on this one. I will color code my top one red and my bottom one green. So now, how would you graph y is less than negative 1/3 x plus 1? Does it look at all familiar? Haley. Do what? Oh, not the green one yet. The red one. Yeah, that's our y, our slope-intercept form, right? So where does this graph start? At 1. Yeah, on the y at 1. How do I use the slope to get to the next point? Down 1 and right 3. That's about all I'm going to be able to fit on there, isn't it? Dashed or solid? Finally a dashed one. All day yesterday's it was all total solid lines, but this one is a dashed. And then you could either use the shortcut, which I don't particularly care for, or can we test 0, 0? Why not, right? It's not on a line. So 0 is less than negative 1/3 times 0 plus 1. 0 is less than 1. Is it? Of course it is. We're shading down here. Like so. Now the green one. We know it's a V because it has absolute value. So first step would be what? I heard somebody say something. Josh, was that you? Where are you going? Yes, exactly. That's your vertex. 1, 0. Good. Then what do? Yeah, help us out. Yeah, use that slope for your right side. Up 2 and over 1. Can only get a couple of those on there. How do you get the left side again? Up 2 and left 1. Now be careful, push your pause button, because is this solid? This one's not solid either. Would it be a good idea to test 0, 0 for that one? Why not, right? It's not on the V. Let's try it. So test 0, 0. 0 is greater than 2 times the absolute value of 0 minus 1. 0 minus 1 is negative 1. What's the absolute value of negative 1? 1. 2 times 1 is 2. Is 0 greater than 2? No. So I can't shade outside the V. I have to shade inside the V. Do you see the teeny itsy bitsy little region that these two will share? I'm going to use blue and really darken this here. That's it. You got to work in there to be a solution to both of these, because that's the only place they overlap, is right there. That's it. Inequalities. I think we've become experts at it. I really do. So we were graphing systems of inequalities, and that was yesterday's. This is today's. And I think there's 2 word problems in this, so I'm probably just going to bring you a sheet of the grid paper that covers the whole thing. And you could use that. Because the word problem numbers don't end up being -10 to 10 numbers.